Every morning, sunlight reaches Earth so gently that we almost forget where it began. It warms our skin, feeds the forests, stirs the oceans, and paints the sky with gold. But that light was not born on the surface of the sun. It began far deeper in a hidden place of crushing pressure, unimaginable heat, and endless motion. At the very heart of our star lies the solar core, a region no spacecraft can visit and no human eye can see. There, in a darkness brighter than anything we know, hydrogen is transformed into helium, mass becomes energy, and the power that sustains life on Earth is created. The sun may look calm from far away, but deep inside, its quiet engine has been working for billions of years. To understand the sun, we must journey inward to the place where daylight is born. Deep inside the sun, beneath every bright layer that can be seen from Earth, there is a region that has never known darkness, yet gives off no gentle glow of its own. It has no surface, no horizon, no landscape, and no boundary sharp enough for any eye to trace. It is not a chamber hidden inside a solid body, because the sun has no solid body. It is a central depth of plasma, pressure, heat, and motion, packed so tightly by gravity that matter behaves in ways far removed from everyday nature. This is the solar core, the hidden engine of the star, and everything that makes the sun important to the solar system begins there. The light that brightens planets, the warmth that moves air and ocean, the energy that supports leaves and living cells. All of it traces its beginning to a place that cannot be reached by spacecraft, touched by instruments, or seen through any telescope. The sun appears from a distance as a smooth and brilliant disk, steady enough to seem simple. But its visible face is only the outer sign of a deeper struggle. Far below the glowing photosphere, below the turbulent layers where hot gas rises and cool gas sinks, the core carries out a transformation that has continued for billions of years. Hydrogen is pressed into helium. A small part of mass becomes energy. Gravity pulls inward, and the energy born in the center pushes back. The result is not stillness, but a sustained balance, one of the most important balances in the history of Earth. The core lies at the center of the sun and reaches outward through roughly the inner quarter of the solar radius. This is a small fraction of the star by size, but it contains the conditions that make the star shine. Outside this inner region, the sun remains vast and hot, yet the pressure and temperature are no longer high enough for fusion to proceed with the same importance. The core is where the sun's identity is decided. It is the place where the star is not merely hot matter, but a working star, a body whose own weight forces its central particles into reactions powerful enough to hold collapse at bay. The photosphere, the layer that sends most visible sunlight into space, is about 5,500 degrees Celsius, yet compared with the core, that surface is cool. At the center, the temperature rises to around 15 million degrees Celsius. At such heat, atoms cannot remain as complete atoms. Electrons no longer stay bound to nuclei in the quiet arrangements that shape rocks, water, air, or living tissue. Instead, matter becomes plasma, a charged sea of bare nuclei and free electrons, always moving, colliding, and responding to electric and magnetic forces. The core is not flame, because flame needs chemical reactions between atoms. It is not fire in the earthly sense. It is matter stripped down and driven by nuclear physics, held under the weight of an entire star. The density is just as strange as the temperature. The core is far denser than common metals, with matter packed into each small volume under crushing pressure. Yet it is not solid. It flows and shifts as plasma. Particles crowd together because gravity leaves them little room. Heat tries to spread matter outward. Gravity tries to draw it inward. Neither side wins completely, and that failure of either side to win is what allows the Sun to exist as a stable star. In this central region, the great question is not only how hot the Sun is, but how it avoids destroying itself. If gravity acted alone, the Sun would contract, its mass would press inward, the centre would grow hotter and denser, and collapse would continue. If outward pressure acted without gravity, the Sun's material would expand away into space. Instead, the Sun rests between those opposing tendencies. The core creates energy through fusion, and that energy contributes to pressure pushing outward. Gravity supplies the confinement that makes fusion possible. The star survives because the two processes are linked. Gravity creates the conditions for fusion. Fusion creates the pressure that resists gravity, and the Sun continues in a long state of controlled endurance. This balance is called hydrostatic equilibrium. The Sun is not sitting still like a stone. It is being held in a vast inward and outward negotiation, renewed moment by moment in its deepest layer. The core's work begins with hydrogen, the simplest and most abundant element in the Sun. A hydrogen nucleus is only a single proton, carrying a positive electric charge. In ordinary conditions, two protons resist coming together because, like charges, repel. They push away from one another before they can touch. The core must therefore do something subtle. It does not merely heat the protons until they smash together easily. Even at 15 million degrees Celsius, the electrical repulsion between them remains a serious barrier. The Sun shines because, in a tiny fraction of encounters, quantum physics allows protons to pass through that barrier in a way that classical motion alone would not permit. This process does not make the core explosive in the familiar sense. It makes it persistent. Fusion events happen rarely for any individual proton, but there are so many protons in the core that rare events become an enormous collective power. Deep within, the Sun's smooth radiance is built from countless small reactions, each one part of a slow and steady chain. The main chain in the Sun is called the proton-proton chain. Step by step, hydrogen nuclei are transformed until helium is formed. Along the way, energy appears in several forms. Some comes as high-energy radiation. Some appears in particles that quickly interact with surrounding matter. Some leaves as neutrinos, almost weightless messengers that pass through the Sun with astonishing ease. The basic outcome is simple enough to state hydrogen becomes helium and a small amount of mass becomes energy. Yet inside that simple result lies the reason daylight exists. The missing mass does not vanish into nothing. It becomes energy according to the deep connection between mass and energy described by Einstein. In the core, this connection is not an abstract idea. It is a daily, stellar process. The Sun is not consuming fuel as a campfire consumes wood. It is changing the identity of atomic nuclei under immense pressure, and the energy released by that change slowly fills the solar system with light. The first light of the core is not the mild yellow glow associated with the Sun from Earth. It begins as fierce, high-energy radiation, born in a place too dense to let it travel freely. A photon created near the centre does not simply fly straight to space. It is absorbed, scattered, re-emitted, redirected, and delayed. Its path becomes a random walk through the Sun's interior, so indirect that the energy released in the core may take hundreds of thousands of years to emerge as visible sunlight. The Sun's brightness is immediate to planets, but ancient in its interior passage. In contrast, neutrinos leave the core almost at once. They interact so weakly with matter that the Sun is nearly transparent to them. They stream out from the central reactions and cross space, carrying information about fusion that is happening now. Their ghost-like passage gives science one of its deepest views into the Sun, not by seeing the core directly, but by catching the particles that escape from it. In this way, the hidden engine is not entirely silent. It sends out clues, and some of those clues move through matter as if matter were almost empty. The core remains unseen, but it is not unknowable. Its existence is written in the Sun's balance, in the steady flow of sunlight, in the measured particles that come from nuclear reactions, and in the slow evolution of the star itself. It is hidden because no material craft can survive such conditions, and because ordinary light cannot carry a clear image outward from the centre. Still, every part of the solar system carries evidence of its work. The planets move through a space shaped by solar gravity and flooded by solar energy. Earth's atmosphere responds to that energy. Oceans store it, plants transform it, and climates are built around its steady arrival. All of this begins in the central darkness of a star. The deepest look inside the Sun is therefore not a view in the usual sense. It is an understanding assembled from physics, particles, pressure, time, and light. It reveals a place where matter is stripped bare, where gravity becomes a furnace without flame, and where the quiet origin of daylight lies buried beneath hundreds of thousands of kilometers of plasma. The solar core is not just the middle of the Sun. It is the first cause of the Sun's visible life, a hidden engine whose work reaches outward until darkness, at last, becomes day. At the centre of the Sun, the most important fact is not heat alone, but resistance. The core is hot because the star is heavy, and the star remains whole because the core is hot. The balance feels steady enough to seem permanent, yet nothing about it is passive. Every layer of solar material presses down on the material beneath it. Above the core lies most of the Sun's mass, a vast depth of plasma drawn inward by gravity. That weight does not rest like stone on stone, because the Sun is fluid, but pressure still rises with depth. Each deeper layer must support everything above it. By the time the centre is reached, the inward pull of the whole star has concentrated matter into a realm where particles are packed closely, moving rapidly and colliding under conditions that allow nuclear fusion to begin. Gravity is therefore not merely a force that threatens the Sun, it is also the builder of the furnace. Without gravity, the hydrogen in the Sun would drift too widely apart to fuse in any meaningful way. Without fusion, gravity would continue its inward work without enough resistance. The Sun is born from the meeting of compression and release, weight and response, collapse and support. This balance is called hydrostatic equilibrium. The name sounds technical, but the idea is quiet and simple. Hydro means fluid, static means steady, and equilibrium means balance. In the Sun, every depth finds a temporary answer to the question of pressure. Gravity pulls plasma toward the centre. Internal pressure pushes plasma outward. Where these two are matched, the star does not rapidly shrink or burst apart. It holds its shape, not because motion has stopped, but because motion is organised around balance. The core becomes the centre of this arrangement, because it is where the pressure is greatest and where the reactions that produce new energy can occur. Fusion releases energy into the surrounding plasma, and that energy helps maintain the outward pressure needed to oppose the inward weight. In this way, the Sun is not supported by a shell, a rigid frame, or any hidden solid. It is supported by the energy of its own centre. The balance is sometimes described as delicate, but it is not fragile in the ordinary sense. It has lasted for billions of years because it contains a kind of self-correction. If the core were to cool slightly, pressure would weaken, gravity would compress the core more strongly. Compression would raise the temperature and density, which would make fusion more active again. If the core were to heat too much, pressure would increase. The central plasma would expand slightly. Expansion would lower the density and temperature, reducing the fusion rate. The Sun therefore has a slow internal thermostat, not a mechanical one, but a natural feedback between temperature, pressure, gravity, and reaction rate. This is one reason the Sun shines so steadily. Its power does not come from an uncontrolled runaway explosion. It comes from a balance in which changes tend to push the core back towards stability. There are fluctuations and waves and deep internal motions, but on the scale that matters for life on Earth, the Sun remains remarkably constant. The pressure inside the core is difficult to imagine because everyday experience offers no close comparison. On Earth, pressure may come from the weight of air, the depth of ocean water, or the load of rock buried under mountains. In the Sun, pressure comes from the weight of an entire star, concentrated inward by gravity. The central plasma is squeezed so intensely that the density becomes far higher than the density of iron or lead on Earth, even though the material remains a gas-like plasma. This strange combination seems contradictory only because ordinary matter is familiar at low pressure. In the core, temperature is so high that atoms cannot form solids, liquids, or familiar gases, yet gravity forces the particles into a packed state. The result is matter that flows like ionized gas but weighs into each small volume like something far denser than metal. It is neither earthly fire nor earthly stone. It is stellar plasma under weight, held where nuclear reactions become the quiet answer to gravity's demand. The outward pressure in the core comes from more than one source. Some comes from the furious motion of particles, because hotter particles move faster and strike their surroundings more forcefully. Some comes from radiation, the energy carried by photons moving through the plasma. In the Sun, particle motion provides much of the support. Each proton, helium nucleus, and free electron contributes to the pressure through its movement. There is no single wall inside the Sun that holds back collapse. There is only the combined effect of countless particles, all restless, all confined, all part of the same vast balance. The core is like a pressure field rather than a place with edges. Moving outward from the center, the pressure and temperature gradually fall. Fusion becomes less frequent. The star transitions into regions where energy is transported rather than newly made. Yet the core remains the anchor, because the rest of the Sun depends on the energy released there. This balance also explains why the Sun has not used its fuel quickly. A more violent process would have consumed the star long ago. The proton-proton chain, the Sun's main fusion path, proceeds slowly because protons repel one another. Only rare encounters lead to fusion, aided by quantum tunneling, the strange ability of particles to pass through a barrier that would otherwise keep them apart. This slowness is essential. The Sun contains a vast amount of hydrogen, but the core converts it at a measured pace. The star's own internal balance keeps the reaction from becoming a sudden detonation. Fusion provides pressure. Pressure moderates compression, and compression shapes fusion. The result is not a blast, but a long luminous lifetime. Stars more massive than the Sun must hold back stronger gravity, and their cores become hotter. Their fusion rates rise sharply, and their lives are shorter. Smaller stars burn more slowly and may last much longer. The Sun sits between these extremes, bright enough to warm planets across a wide region, but not so massive that it rushes through its central hydrogen. Its balance helps give Earth a long, stable era in which oceans, climates, and life can develop. The same equilibrium also explains how the Sun becomes a star in the first place. It begins as part of a cold cloud of gas and dust in space. Gravity draws a portion of that cloud inward. As the material falls together, its center grows denser and hotter. Eventually, the center becomes hot and dense enough for hydrogen fusion to begin. Once fusion starts at a sustained rate, the young sun reaches a new balance. The pressure produced by its core slows the contraction, and the star settles into the main sequence phase. The sun's present calm therefore comes from an ancient transition, when collapse finds a counterforce and a star becomes stable. Yet equilibrium does not mean the sun is finished changing. The balance is real, but it shifts as fuel changes. In the core, hydrogen slowly becomes helium. Helium does not fuse under the sun's current central conditions in the same steady way, so it accumulates. As helium builds up, the composition of the core changes. Gravity responds by compressing the core slightly, and fusion in the remaining hydrogen becomes more intense. The sun gradually grows brighter across its main sequence life. This change is too slow to notice across generations, but it matters across planetary history. Equilibrium is not a frozen state, it is a moving balance, a sustained negotiation that changes its terms while continuing to hold the star together. Far in the future, the balance will shift more dramatically. When the central hydrogen becomes too depleted to support the sun in its present form, the core will contract, outer layers will expand, and the star will leave the calm pattern that now defines it. But that distant transformation only makes the present balance more remarkable. For now, the sun's core keeps answering gravity with pressure. It does so without sound, without flame, without any visible boundary between struggle and calm. The visible sun seems smooth from Earth because the battle underneath is not chaotic enough to tear it apart. It is measured by physics, guided by feedback, and spread through a body so large that its changes are slow. At the deepest level, the sun is a star because it does not surrender to its own weight. It bends inward until the center grows powerful enough to push back. In that push and pull, daylight becomes possible. The warmth reaching Earth is not merely energy from a hot object. It is the outward sign of a balance held in the hidden center, where gravity presses down through the mass of a star and fusion answers from the dark. In the deepest part of the sun, fusion begins in a place where the ordinary rules of chemistry have already disappeared. There are no complete atoms in the core, no molecules, no glowing embers, and no burning surface. Heat has stripped electrons away from nuclei, leaving a plasma of charged particles moving under immense pressure. Among these particles, hydrogen nuclei are the most important. Each one is a single proton, simple in structure yet difficult to merge with another. The sun contains an enormous supply of hydrogen, but abundance alone does not make starlight. For hydrogen to become helium, protons must come close enough for the strong nuclear force to take hold. This force binds atomic nuclei, but it works only across extremely short distances. Before two protons can reach that closeness, they must face their electrical repulsion. Both carry positive charge, so they push apart. The core is therefore not only a furnace, it is a place where nature must overcome resistance at the smallest scale. The temperature gives particles speed, and the pressure keeps them crowded. Yet even there, most proton encounters end without fusion. They pass near one another, feel the repelling force, and separate again into the plasma. The miracle of the sun is not that every collision becomes energy. It is that, among countless collisions, enough succeed to keep a star alive. The main path is the proton-proton chain, a sequence of nuclear reactions suited to stars like the sun. It begins with two protons meeting under core conditions. In the rare encounter that succeeds, one of the protons changes into a neutron through the weak nuclear force. The two particles then form a nucleus of heavy hydrogen, known as deuterium. This first step is slow because it requires more than simple contact. It requires one proton to change its identity, releasing a positron and a neutrino. The positron soon meets an electron in the surrounding plasma, and their meeting turns their mass into radiation. The neutrino, far less social with matter, begins its swift escape from the sun. This first step is the narrow gate through which solar fusion must pass. Because it is difficult, it regulates the sun's pace. If protons fused easily, the sun would burn through its central fuel far more quickly. Instead, the weakness of this first reaction helps give the star its long life. After deuterium forms, the next step happens much more readily. A deuterium nucleus can capture another proton and become a light form of helium, called helium-3. This reaction releases energy in the form of a gamma ray, a photon far more energetic than visible light. The gamma ray does not travel freely for long in the dense interior, but its energy has entered the solar material. From there, the chain continues. In the most common branch, two helium-3 nuclei eventually meet and combine together. They form helium-4, the stable helium nucleus familiar from the final result of the sun's main fusion process. Two protons are released back into the plasma, ready to take part in later reactions. The chain has therefore converted hydrogen into helium, but not by a single simple collision. It has passed through steps, delays, transformations, and branches, each governed by the forces that shape atomic nuclei. The net result is often described plainly. 4 hydrogen nuclei become one helium nucleus, with energy released. This statement is true, but the inner path matters because it reveals why the sun shines with such patience. Fusion is not a wild rush of every available proton. It is a selective process, filtered by electrical repulsion, quantum tunneling, and the rare operation of the weak nuclear force. Quantum tunneling gives some particles a chance to cross a barrier they do not have enough classical energy to climb. In everyday language, the particles do not smash through the barrier like stones through glass. Rather, their wave nature allows a small probability that they will appear on the other side of the repulsive barrier, close enough for nuclear binding to begin. The probability is tiny for any one pair of protons, but the core contains so much matter that tiny probability becomes great power. The sun's calm brightness is built on a nearly impossible event, repeated across an immense population of particles. Energy emerges because the final helium nucleus has slightly less mass than the separate particles that led to it. The missing mass has not been destroyed, it has become energy, following the relation between mass and energy that underlies nuclear physics. In the core, this conversion is continuous. It does not require a large loss of mass from each reaction. A very small difference is enough because the number of reactions is so vast. Each second, the sun converts a portion of its mass into energy, not as a sign of failure, but as the natural cost of shining. The star is massive enough that this loss is tiny compared with the whole sun. Yet the energy released is enormous from the perspective of planets. That energy begins as motion, radiation, and particles inside the core. It helps maintain pressure, warms the plasma, and starts the long outward journey that will eventually become sunlight. The proton-proton chain also produces neutrinos, and these particles are crucial because they leave the core almost immediately. They carry away a small part of the energy and a direct record of the reactions that made them, while photons are trapped in the dense solar interior and scattered for ages. Neutrinos pass through the sun as though most of it were empty. They're difficult to detect on Earth, yet their presence confirms that fusion is taking place in the deep center. In this way, the first steps of the chain send 2 kinds of messages. One message becomes light only after a long passage through the star. The other message escapes at once, faint and ghost-like, offering a nearly direct report from the core. The Sun's fusion is also self-limiting through the structure of the chain. Since the first proton-proton step is slow, the core does not release all possible energy at once. The reaction rate depends strongly on temperature and density, but the feedback of the star keeps it moderated. If the core compresses and heats, fusion becomes more active, raising pressure and encouraging expansion. If the core expands and cools, fusion slows, letting gravity compress it again. The chain therefore participates in the same balance that holds the Sun steady. It is both the source of energy and part of the mechanism that prevents the star from racing out of control. The result is a star whose visible brightness changes only modestly across human history, even though its center is filled with nuclear reactions. There is a quiet strangeness in the fact that something as gentle as daylight begins with particles changing identity inside a plasma so hot that ordinary matter cannot exist. The warmth that reaches a leaf is connected to protons that once resisted one another, then fuse through a chain of rare events in the central Sun. The yellow light that falls on ocean waves is the softened descendant of high-energy radiation born far below the surface. By the time it reaches Earth, the violence of scale has been transformed into steadiness. The core does not glow for observers like a lamp behind glass. It works invisibly, releasing energy into surrounding matter, feeding the star from within. In every moment, the proton-proton chain turns the simplest element into a slightly heavier one, and the difference becomes the power of the solar system. Its quietness is one of its deepest mysteries. The core is more energetic than any place in the solar system, yet each small volume releases power at a modest rate compared with many earthly engines. The greatness comes from size. A slow reaction spread through a vast central region becomes a star. This slow pace is why the Sun can shine across billions of years rather than flare briefly and vanish. This is the beginning of solar light, not at the surface where brightness escapes, but at the center where hydrogen first changes. Fusion begins in darkness, under the weight of the Sun, in rare meetings between particles that almost always fail. From those rare successes comes a flow of energy old enough to shape worlds and steady enough to make life possible. The solar core can seem, from a distance, like the site of an endless explosion, a place where nuclear power must be raging with the violence of a bomb that never finishes going off. The truth is quieter and stranger. The Sun does not shine because its center is tearing itself apart. It shines because its center is restrained. Fusion in the core is powerful only because it is spread through an immense volume of matter and sustained across deep time. At the level of individual particles, the process is slow, difficult, and highly selective. Most protons in the core never fuse during any given moment. They move, collide, repel, scatter away, and continue their restless motion. The core is filled with encounters that almost succeed but do not. Out of an unimaginable number of meetings, a tiny fraction becomes nuclear change. That tiny fraction is enough, because the Sun contains so much hydrogen, and because the central conditions continue without pause. What looks from the outside like effortless brightness is, inside, a patient statistical process. The Sun is not an explosion held in a shell. It is a vast balance in which nuclear reactions happen slowly enough for gravity and pressure to remain in conversation. This matters because explosions are defined by runaway release. A chemical explosion on Earth spreads because heat makes nearby fuel react faster, and that speed drives still more reaction. A nuclear weapon releases energy through an abrupt chain reaction that grows on a timescale far too short for balance to moderate it. The Sun behaves differently. Its main fusion path depends on the proton-proton chain, and the first step of that chain is naturally slow. Two protons must come close despite their mutual electrical repulsion, and then one of them must change into a neutron through the weak nuclear force. This is not a common event. The weak nuclear force earns its name in this context, because it does not make the reaction easy. The difficulty of that first step acts like a deep natural brake on the Sun. It prevents the core from burning through hydrogen suddenly. It turns nuclear possibility into long endurance. The core is therefore powerful because it is inefficient in just the right way. A perfectly eager fusion process would be disastrous for a star like the Sun. The steady daylight of Earth depends on the reluctance of protons to fuse. Another reason the Sun does not behave like an explosion is that it is not assembled from fuel and spark in the familiar sense. The core is already hot. Its plasma is already moving rapidly. The issue is not whether the material catches fire. There is no fire to catch. There are no intact atoms passing electrons between chemical bonds. The energy comes from nuclear binding, from the way particles are held together inside atomic nuclei. Hydrogen fuses into helium because the final arrangement is more tightly bound, and the difference in mass becomes energy. But this happens only under conditions created by gravity, and gravity remains present as a controlling partner. If the core produces slightly more energy, pressure rises and the central plasma can expand a little. That expansion lowers temperature and density, which slows fusion. If the core produces slightly less energy, gravity compresses the plasma more strongly. Compression raises temperature and density, which encourages fusion. The star has no mind and no machinery, yet its structure forms a slow feedback system. It does not explode because the same physics that powers it also pushes it back toward balance. The word calm must be used carefully here. The core is not calm in the sense of stillness. Particles rush through plasma at enormous speeds. Radiation is produced, absorbed, redirected, and degraded. Free electrons and nuclei respond to electric forces. Pressure is beyond ordinary imagination. Yet the large-scale outcome is calm compared with catastrophe. The Sun's brightness changes little from one human lifetime to another because its interior reactions are buffered by the star's own size and structure. This is one of the great differences between local violence and global stability. On small scales, the core is intensely active. On the scale of the whole star, it is regulated. The Sun can be turbulent in its outer layers, with magnetic fields twisting and eruptions sending material into space. But the core itself maintains the slow production that underlies everything else. Its power is not a shout. It is a long, deep pressure, sustained by the immense number of particles taking part. The comparison with a human-made fusion reactor also reveals the core's unusual nature. On Earth, controlled fusion is difficult because plasma must be heated and confined without the natural weight of a star. Engineers use magnetic fields or brief compression to hold fuel long enough for reactions to occur. The Sun has a simpler and far larger method. It uses gravity. The mass of the star confines the core from every direction. Yet even with this natural confinement, the Sun's fusion is not rapid in each small portion of material. A small volume of the solar core produces energy at a modest rate compared with many earthly heat sources. This surprises many accounts of the Sun, because the total output of the star is enormous. The explanation is scale. A modest rate multiplied by the huge central region of a star becomes a flood of power. A candle may seem brighter per small amount of material than a similar small volume of the core. But a candle is brief and tiny. The core is vast and continuous. It does not need each part to be frantic. It needs the whole to be steady. There is also a deep slowness hidden in the life of a proton. A single proton in the core may wait an immense span of time before taking part in a successful fusion event. It simply moves through the plasma, colliding and scattering until probability eventually allows a rare transformation. The sun can shine because the core contains so many particles that individual delay is irrelevant to the collective result. A process can be almost impossibly unlikely for one particle and still inevitable for a star. Nature often builds vast certainty from tiny probabilities repeated over enormous numbers. The core's energy is not immediately released into space either. Even after fusion creates high-energy photons, the surrounding plasma traps them in a long random passage. A photon may travel only a short distance before interacting with another charged particle, then appear again in a new direction, at a different energy, part of a long process that gradually transforms harsh gamma radiation into the softer light that later escapes from the surface. This delay further separates the core from the image of an explosion. In an explosion, energy rushes outward through a rapidly expanding system. In the sun, energy born in the core is absorbed into the star's interior and passed outward through countless interactions. The star stores, scatters, softens, and delays its own light. The outer glow is the patient result of a buried nuclear process, not the immediate flash of central fire. The same restraint allows planets to exist in long stability around the sun. If the core were prone to sudden runaway changes, the solar system would not receive a steady flow of energy. Earth's atmosphere, oceans, and life depend not only on the fact that the sun shines, but on the fact that it shines consistently enough for complex systems to persist. The core gives energy in a way that is enormous yet measured. Its slowness becomes habit for the planets. Days follow nights. Seasons follow their cycles. Climate responds to solar power across oceans and continents. Beneath all of this lies the hidden improbability of proton fusion, the rare success of particles inside a central plasma. The sun seems simple because its light arrives smoothly, but that smoothness is the outward face of a regulated nuclear interior. The core is therefore not a cosmic bomb held in suspense. It is a natural reactor, but even that phrase can mislead if it suggests machinery or rigid walls. The sun has no reactor vessel. Its confinement is gravity. Its fuel is central hydrogen. Its regulator is feedback, and its timescale is billions of years. It remains luminous because fusion is difficult, not because fusion is easy. It survives because every surge in pressure has a response. Every cooling has a counter-response, and the reactions themselves proceed through a narrow gate. In the heart of the sun, power appears most clearly as patience. The deepest energy in the solar system is not born from sudden destruction. It is born from rare meetings, repeated endlessly, under weight that neither wins nor loses. The result is the steady star overhead, not an explosion, but a long equilibrium shining outward from the dark. Beneath the sun's visible face, the idea of matter begins to lose its familiar shape. The core is not solid, though it is pressed more tightly than metals. It is not liquid, though it flows under pressure. It is not gas in the ordinary earthly sense, though it has no fixed form and fills the space available to it. It is plasma, the state of matter that appears when heat and energy strip atoms apart. In the solar core, electrons are no longer bound around nuclei in neat arrangements. They move freely through a crowded sea of charged particles, while bare hydrogen and helium nuclei rush among them. This is matter unbuilt, matter pushed beyond the quiet architecture of atoms. Yet it is not disorder without pattern. Its behavior is shaped by gravity, heat, electric charge, radiation, and the constant pressure of everything above it. The core is a place where no familiar surface can exist, because every possible surface would be torn into charged particles and folded into the surrounding plasma. It is a depth rather than a landscape, a central condition rather than a room. Its strangeness comes from the union of two extremes that rarely belong together in human experience. It is incredibly hot, and it is incredibly dense. On Earth, heating usually makes matter expand and become less dense. Air warms and rises, metal melts, water becomes vapor. In the core of the Sun, heat pushes outward, but gravity presses inward with the weight of the star. The result is an environment where particles move with enormous energy while also being forced into close quarters. The core reaches temperatures of around 15 million degrees Celsius, far beyond the point where atoms can remain whole. At the same time, its density rises to roughly 150 grams per cubic centimetre, which means a small volume of core plasma contains far more mass than the same volume of iron or lead under ordinary conditions. This does not make the core a solid object. Solidity depends on atoms and bonds, on structures that cannot survive there. The core is dense because gravity crowds the particles. It remains plasma because heat prevents them from settling into any fixed arrangement. Every particle in the core exists within a field of pressure. There is no empty gap like the spaces imagined between objects in everyday life. Even though atoms themselves are gone, the particles left behind are abundant and restless. Protons repel other protons through electric charge. Electrons weave through the plasma, attracted to positive nuclei but too energetic to become bound in stable orbits. Radiation moves through the same region, but not cleanly. Photons are absorbed and scattered by charged particles almost as soon as they are born. Nothing travels far without meeting something else. The core is therefore not only a place of heat, it is a place of continual interruption. Motion is intense, but paths are short. Particles and radiation are always redirected, and from this dense confusion the star builds a steady outward flow of energy. The pressure at the center is not simply an added detail. It is the reason the core can do what it does. Without such pressure, the heat would spread the plasma apart and fusion would fade. With gravity compressing the Sun from all sides, particles are kept close enough for rare nuclear reactions to occur. Hydrogen nuclei still resist one another because they carry the same positive charge. But pressure and temperature create enough close encounters for quantum tunneling to matter. The core is where the Sun gives probability an enormous stage. In a small laboratory sample, such rare events would be negligible. In the heart of a star, they become destiny. Dense plasma makes the proton-proton chain possible. Not because it removes the barrier between protons, but because it creates uncountable attempts. Fusion emerges from repetition under weight. It is the slow success of a process that almost always fails. Plasma also allows the core to respond as a whole. Since the material is fluid, it can expand or contract slightly as conditions change. If the core heats and pressure rises, the plasma pushes outward. If energy production drops, gravity squeezes inward. This ability to move is part of the Sun's stability. A rigid core would crack or store stress differently, but the Sun has no rigid center. Its deepest material adjusts through motion, pressure, and temperature. The core breathes only in the broadest physical sense, through small changes spread across immense scales. But those changes help keep fusion from running away. The plasma is not peaceful, yet it is flexible. It can transmit pressure, scatter radiation, carry charged particles, and maintain the environment that fusion requires. Its lack of solidity is not weakness. It is one reason the star can remain balanced. The density of the core also shapes the first journey of energy after it is created. Gamma rays born from fusion do not escape like beams from a lamp. They enter a crowded plasma where charged particles lie in every direction. A photon may be absorbed by an electron or scattered from it, then reappear in another direction with changed energy. Over time, the original energy is spread, shared, and softened. The core is therefore the beginning of transformation, not the final form of sunlight. Energy made as harsh radiation becomes part of a larger thermal sea. It is mixed into the star, held within the dense interior, and released outward only through a long chain of interactions. The pressure that helps create fusion also delays the escape of its light. The sun shines steadily partly because its interior is so thick to radiation. The core does not give its energy away immediately. It lends it to the surrounding plasma, and the star passes it outward with extraordinary patience. In this dense charged environment, magnetism and electricity are never entirely absent, because moving charge particles naturally create electromagnetic behavior. The core, however, is not usually imagined as the dramatic source of the sun's visible magnetic storms. Many of the magnetic structures that shape sunspots, flares, and eruptions are tied to motions in outer layers where plasma circulates more strongly. Still, the same basic nature of plasma runs through the star. The sun is made of charged matter, and charged matter is never simple. It responds to fields, carries currents, and couples motion to energy. The core's role remains deeper and steadier. It provides the energy that later travels into regions where convection, rotation, and magnetism give the sun its changing face. The calm disk seen from far away is therefore the outer expression of many hidden layers. With the dense core at the base of the chain, to call the core hot is true, but it is incomplete. Heat describes particle motion, while pressure describes confinement. The core is extreme because the two exist together. If there were only heat, the plasma would expand into space. If there were only weight, matter would collapse inward. In the sun, each extreme holds the other in check. The particles are free from atoms, yet not free from gravity. They are moving furiously, yet held in a compressed central region. This combination makes the sun unlike anything within ordinary reach. It is not a burning ball in the old sense. It is a self-gravitating sphere of plasma, with a core dense enough to force nuclear possibility into reality. The absence of solid ground makes it more mysterious, not less. There is no floor on which the engine rests. The engine is the condition itself. The solar core also reminds science that visibility is not the same as importance. The photosphere is what telescopes see in visible light, and the corona stretches outward in a ghostly atmosphere, but the core sets the terms for all of it. It is hidden by the very density that makes it powerful. Ordinary light cannot carry a clear image from that depth, because the plasma scatters it beyond recognition. No probe can descend, because any material structure would be destroyed long before approaching the central region. The deepest knowledge of the core must come indirectly, from mathematics, solar vibrations, neutrinos, and the star's steady output. In that indirectness lies part of the quiet wonder. The core cannot be visited, yet it is not remote from life. Its pressure is written into daylight. Its plasma shapes the warmth that crosses space. Its dense, formless matter is the unseen beginning of weather, photosynthesis, and the long habitability of Earth. In the center of the sun, there is no ground, no flame, no ordinary atom, and no empty silence. There is only plasma underweight, crowded by gravity and stirred by heat, making possible the rare nuclear meetings that keep a star alive. From this charged and buried sea, the sun's power begins its long outward transformation. At the edge of the solar core, energy has already been born, but it is nowhere near escape. The newborn radiation is not the warm gold of daylight, and it does not stream outward in a clean beam. It begins as high-energy photons, often gamma rays, produced in nuclear reactions and in the restless meetings of particles within the plasma. A gamma ray carries far more energy than visible light, but in the deep sun, energy alone does not mean freedom. The surrounding matter is so dense, so full of charged particles, that a photon can rarely travel far before it is interrupted. It is scattered by an electron, absorbed and re-emitted, redirected into a new path, or changed in energy as it becomes part of the star's wider thermal sea. The core creates light, yet the core also traps it. From that first moment, the photon enters a maze with no walls, no corridors, and no fixed direction, a maze made entirely of matter, pressure, and chance. The journey outward is called a random walk. This phrase is gentle, almost casual, but inside the sun it describes an immense delay. A photon does not know the surface. It has no memory of its former path and no preference for the direction of space. After each interaction, it may be sent outward, inward, sideways, or back toward the center. The average progress away from the core is therefore extremely slow. It is like motion hidden inside hesitation, a series of tiny steps that only becomes an outward journey when counted across enormous time. The sun's radius is vast, but the photon does not cross it as a traveller crosses open air. It must pass through layer after layer of plasma that remains opaque to its passage. In the radiative zone, above the core and below the outer convective region, energy moves mainly by radiation. But radiation here does not mean easy flight. It means transfer through repeated absorption and emission, with each event slightly reshaping the energy that began in the core. The radiative zone occupies a great middle depth of the sun. It is less extreme than the core, but still dense and hot beyond ordinary experience. Fusion is no longer the main source of energy there. Instead, the zone receives the energy made below and carries it outward by the interaction of photons with plasma. The material in this region is stable enough that large-scale overturning does not dominate. Hotter, deeper material does not simply rise in huge currents through the entire zone. Instead, energy leaks through radiation, step by step, encounter by encounter. The word leak is useful because the process is not swift. The photon's path is constantly broken, and the original gamma ray is gradually transformed. Its energy is shared among many particles and many photons. By the time the sun finally releases light from its surface, the energy that began as harsh radiation has been softened into a broad range of wavelengths, including the visible light that reaches planets. The photon that emerges from the photosphere is not the same individual photon in any simple sense as the one born in the core. It is better to think of the energy as being passed along, divided, absorbed, and recreated through an immense chain of interactions. The identity of a single photon becomes less important than the survival of the energy flow. Solar energy moves outward like a message copied so many times that no original paper remains. Yet the meaning continues. The core writes the first line in gamma radiation. The radiative zone rewrites it again and again in the language of heat. Eventually, after a long delay, the outer sun speaks it as visible light. This transformation is one reason the sun appears steady. The dense interior acts like a deep reservoir, smoothing sudden changes from the center before they could reach the surface. Energy does not simply burst through. It is stored, mixed, delayed, and released through the star's structure. Estimates for this inner journey vary because the process is complex, but it may take hundreds of thousands of years for energy produced near the core to work its way to the outer layers. That span is longer than the existence of modern civilization, and long enough to change the meaning of sunlight. The light that crosses space to Earth in only minutes carries energy that began its outward struggle in a sun whose interior held it long before human memory. In the photon maze, time is not measured by distance alone. A path that could be crossed quickly in empty space becomes ancient when every step is interrupted. The sun is transparent to some messengers, such as neutrinos, but it is deeply opaque to its own light. This opacity is not a failure of the star. It is part of its nature. The charged particles of the plasma interact strongly with electromagnetic radiation, and photons are electromagnetic radiation. The same matter that fusion heats also becomes the matter that delays the heat's escape. In the deep sun, brightness is trapped by the very material it warms. The radiative zone is therefore a place of patience on a scale difficult to hold in thought. Nothing there resembles a ray of sunlight passing through a clear window. Instead, energy diffuses, and diffusion is slow because each movement outward is only a slight statistical preference emerging from countless direction changes. A photon may make progress, lose it, and make it again, while the larger energy current continues outward because the core is hotter than the layers above it. Heat flows from hotter regions toward cooler ones. Even when individual paths are chaotic, the maze has no guide, yet the temperature gradient gives the whole process direction. Deeper layers are hotter, outer layers are cooler, and so energy gradually migrates away from the center. This is not purposeful motion. It is the statistical outcome of many random exchanges. The sun's interior turns disorder into a steady flow because there are so many interactions that the average result becomes reliable. In that average lies the path of daylight. The photon maze also changes the quality of the energy. Gamma rays born in or near the core do not remain as a pure stream of gamma rays. Through repeated interactions, energy is redistributed into lower energy photons. The final sunlight escaping from the photosphere contains visible light, infrared radiation, and other wavelengths, reflecting the temperature of the surface layer rather than the direct temperature of the core. This is why the sun's surface can appear as a glowing disk rather than as a blast of lethal core radiation. The outer light carries the core's energy, but it carries it after long processing by the star. The sun is not merely a source, it is also a transformer. It receives nuclear energy in its deepest region and turns it, through delay and diffusion, into the stable radiance that shapes the solar system. Above the radiative zone, the method of transport changes. Farther outward, the plasma becomes opaque in a different way, and convection begins to dominate. Hot material rises, cooler material sinks, and energy is carried by the motion of matter itself. But before that outer churning begins, the photon maze has already done much of the work of slowing and softening the core's radiation. The radiative zone is quieter in appearance than the convective layers, but its quietness hides an enormous number of interactions. It is a depth of invisible exchange, where light is never allowed to remain a simple beam. Each scattering event is small. Together they build the long delay between fusion and sunlight. Because of this delay, the surface brightness of the sun is both present and ancient. It is present because the photons leaving the photosphere begin their free journey at that moment. It is ancient because the energy they carry was created far below, long before it could emerge. The photon maze separates birth from arrival. It turns the sun into a keeper of its own past, releasing energy that has spent ages inside the star. There is a quiet beauty in this delay. The light that seems immediate is the end of a hidden migration. The warmth that reaches a planet has passed through a central furnace, a radiative labyrinth, and an outer sea of moving plasma before it enters open space. The deepest look inside the sun therefore reveals not only where energy begins, but how hard it is for that energy to leave. A star shines because fusion creates power, yet it shines steadily because that power is forced to wait. In the dense interior, Daylight is not born and released in the same breath. It is born, scattered, forgotten, remade, and slowly carried outward through a maze of plasma until, after immense time, it finally becomes free. For a ray of sunlight, freedom begins at the photosphere, yet its story has already grown ancient before it reaches that bright edge. The energy that leaves the sun as visible light is not newly made at the surface. It has been carried upward from the deep interior, changed by collisions, absorbed into plasma, re-emitted, scattered, and shared until the fierce radiation of the core becomes the softer glow that can cross space. At the photosphere, the outer visible skin of the sun, the long confinement ends. A photon finally finds a direction clear enough to continue. Behind it lies a journey through dense layers where straight paths are broken almost as soon as they begin. Ahead of it lies open interplanetary space, thin and dark compared with the crowded interior it has escaped. The contrast is immense. For hundreds of thousands of years, energy may wander through the sun's inner maze. Once it leaves the surface, it takes only about 8 minutes to reach Earth. The last passage is brief, almost effortless, yet it carries the memory of an earlier delay so long that sunlight becomes both fresh and ancient at the same time. This difference between the inner journey and the outer crossing reveals how strange the sun truly is. In empty space, light moves at the fastest speed nature allows. It crosses great distances with no need for a medium, no air, no wire, no carrying material. Between the sun and Earth, most of the path is vacuum, filled only with sparse particles, fields, dust, and the flowing solar wind. Across that emptiness, sunlight moves in a direct outward stream. It does not need to push through walls of plasma. It does not continually lose its direction. It leaves the photosphere and expands into a widening sphere, spreading over the orbits of planets, asteroids, and comets. By the time a small part of that light reaches Earth, it has crossed a distance so large that ordinary travel makes it seem unreachable. Yet for light, the crossing is measured in minutes. The sun is far away by human scale, but close by astronomical scale. Its light arrives quickly enough that the bright disk appears almost immediate, even though every sight of the sun is a glimpse of its state about 8 minutes earlier. That delay is small compared with the inner history of the energy, but it is still real. Light, heat, and the visible signs of surface activity all arrive after crossing the gulf between star and planet. Space preserves a narrow distance in time, yet the greater delay belongs inside the star. Before a photon can begin its short interplanetary flight, the energy it carries has spent ages beneath the surface, unable to escape because the solar interior is opaque. The sun is near enough for its light to sustain life, but deep enough within itself to hide the origin of that light across spans longer than civilizations. There is a quiet paradox here. Daylight feels immediate because it arrives each morning with the turning of Earth, but the energy within it began its outward passage far earlier than the day itself, far earlier than the season, far earlier than the human moment receiving it. The sun's surface releases it only after the interior has delayed and transformed it. The final 8-minute crossing is therefore not the main journey of sunlight. It is the release after captivity. The light that reaches Earth is like a message that spends ages being passed hand to hand through a crowded city, then suddenly emerges onto an open road and travels with perfect speed. In the sun, however, the message is energy itself, converted from mass in the core, reshaped by plasma, and set free at last from the photosphere. The photosphere is often called the surface of the sun, but it is not solid ground. It is the layer from which most visible light escapes into space. Below it, the plasma is more opaque. and photons are likely to be absorbed or scattered. Above it, the solar atmosphere grows more transparent. The boundary is therefore a boundary of escape, not a hard edge. It marks the depth where light can finally travel outward without being immediately swallowed back into the sun. From there, the photon joins the great outward flow known as solar radiation. It moves away from the star in all directions, and only a tiny fraction ever intersects Earth. Most sunlight goes elsewhere, slipping into space, passing beyond planets, fading with distance as it spreads. Yet the small fraction that meets Earth carries enough power to shape the surface of a world. It warms oceans, drives evaporation, stirs winds, powers photosynthesis, and sets rhythms for countless forms of life. A reaction between particles in the solar core becomes the energy of weather and living systems. The transformation is slow inside the sun, quick across space, and then slow again as Earth absorbs, stores, reflects, and redistributes the incoming light. Oceans hold heat for seasons and years. Ice reflects part of it back to space. Forests turn a portion into chemical energy. The brief flight from the sun ends in a planet full of delays of its own. This chain makes every daylight moment part of a much longer history. The photon that enters the open sky has already survived the hidden depths of a star. It comes from a process so remote that no direct image can trace it backward. By the time it reaches the top of Earth's atmosphere, it has become ordinary in appearance. One part of the broad river of sunlight. Some of it scatters in the air, making the sky bright. Some reaches land and water. Some reflects from clouds. Some is absorbed and later released as infrared radiation. Its first origin, however, remains in the core, where hydrogen nuclei once passed through the narrow gate of fusion. The journey makes the sunlight gentle enough for life because the sun has transformed its core energy before releasing it. Raw core radiation would be destructive, but the layered star turns that energy into a spectrum that includes visible and infrared light. Distance reduces its intensity further, spreading the star's power across a sphere of space. Earth receives not the center's violence, but its moderated gift. The 8-minute travel time also gives a simple way to feel cosmic scale without losing calm. Light is the fastest messenger, yet it still needs time to cross from sun to Earth. The space between star and planet is not empty distance in an abstract sense. It has width enough that even light requires minutes to pass through it. The sun may dominate the sky, but it is not touching Earth directly. It sends energy across a gulf, and that gulf is part of what makes the energy bearable. The ancient inner delay and the brief outer crossing meet at every dawn. When the sun rises over a horizon, what appears is not energy freshly made in that moment. It is the arrival of a long-concealed process. The core has fused hydrogen. The radiative zone has slowed the energy. The convective zone has carried heat upward by moving plasma. The photosphere has released light, and space has delivered it with startling speed. The visible sunrise is only the last gesture in a chain mostly hidden from sight. Its beauty comes partly from that hiddenness. A simple glow on cloud or ocean is connected to the deep physics of matter under pressure. The everyday brightness of morning is the far end of a path through the center of a star. This is why the deepest look inside the sun changes the meaning of sunlight. It no longer appears as a surface phenomenon alone. It becomes a record of transformation across radically different realms. In the core, energy is born from nuclear fusion. In the radiative zone, it wanders in confusion in the outer layers. It is carried and released. In space, it streams freely. On Earth, it becomes warmth, color, motion, and life. The same energy moves through all of these identities without needing a visible thread to connect them. The The sun's gift is therefore layered with time. It is minutes old in space, perhaps hundreds of thousands of years old in its solar passage, and rooted in nuclear reactions that belong to the ongoing life of a star billions of years old. The final crossing from sun to earth is fast, but it is not small in meaning. It completes the journey from hidden core to living world. It turns central pressure into surface warmth, nuclear change into daylight, and ancient delay into the present brightness of a planet. The light arrives quietly, without carrying the story on its face. Yet within that quiet arrival is the long memory of the sun energy born in darkness, held in plasma, freed at the surface, and delivered across space in 8 minutes after ages. Beyond the long maze of photons, another kind of messenger leaves the solar core almost without delay. It is not bright in the ordinary sense, and it does not warm a surface as sunlight does. It moves through the star with such little resistance that even the dense central plasma is nearly transparent to it. This messenger is the neutrino, one of the quietest particles in nature and one of the most important clues to the hidden life of the sun. Neutrinos are born during nuclear reactions in the core, especially in the first steps of the proton-proton chain. When one proton changes into a neutron and a new light nucleus begins to form, that change releases a neutrino, and almost at once the particle is on its way outward. While photons are scattered, absorbed, and remade through immense spans of time, neutrinos pass through the solar interior as though the star is almost empty. They cross the radiative zone, the convective zone, and the visible surface without being caught in the crowd of charged particles. Then they continue into space, spreading through the solar system in a thin, ghost-like flood. The difference between photons and neutrinos is one of the deepest contrasts inside the sun. A photon is a carrier of electromagnetic energy, and the sun is made of charged particles that interact readily with electromagnetic radiation. This is why light born in the core cannot escape directly. A neutrino, however, feels neither the electromagnetic force nor the strong nuclear force in any ordinary way. It interacts mainly through the weak nuclear force and gravity, and the weak force acts only across tiny distances. For most matter, this makes the neutrino almost untouchable. It can pass through plasma, rock, metal, ocean, atmosphere, and living tissue with little chance of meeting anything at all. Vast numbers of solar neutrinos cross Earth every moment. Most continue through the planet and leave on the other side unchanged, silent, and unnoticed. Their very indifference to matter is what makes them valuable. They are hard to detect, but because they escape so cleanly, they carry a nearly direct report from the solar core. In a sense, neutrinos give the sun two clocks. The clock of light is delayed. The visible sunlight reaching space has energy that may have wandered inside the star for hundreds of thousands of years before escaping. It tells of the core indirectly, after a long process of absorption and re-emission has erased any simple memory of the first photon. The clock of neutrinos is immediate by comparison. A neutrino made in the core needs only a short time to cross the sun, and then about 8 minutes to travel from the sun to Earth. It tells of fusion as it is happening now, not as energy processed through the deep interior. This immediacy gives neutrino astronomy a special power. Since no spacecraft can enter the sun, and no ordinary telescope can see the core must be studied by what escapes from it. Photons from the visible surface speak for the photosphere. Solar vibrations reveal how sound waves move through the interior. Neutrinos speak from the nuclear furnace itself. Detecting them is difficult because their weakness is also their gift of escape. A particle that almost never interacts cannot be caught easily. Neutrino detectors therefore rely on enormous amounts of material and careful patience. Some use vast volumes of water, heavy water, or special liquids buried deep underground, where rock shields them from many other kinds of cosmic particles. When a rare neutrino finally interacts inside such a detector, it may produce a faint flash of light or a small signal that can be separated from background noise. Most passing neutrinos leave no trace, but the few that do are enough to build a picture over time. The detectors do not see the core as an image, they count whispers from it. Each event is small, but together they reveal the rate and nature of fusion inside the Sun. They show that hydrogen really is being transformed into helium in the hidden center, and that the energy supporting the Sun comes from nuclear reactions rather than chemical fire or gravitational collapse alone. The story of neutrinos is therefore also a story of trust in indirect evidence. Science often reaches places that cannot be visited by following consequences with care. The solar core is hidden behind layers of opaque plasma, yet the neutrino flow has a pattern expected from fusion. The numbers, energies, and types of neutrinos give information about the reactions that create them. Lower energy neutrinos come from the common branches of the proton-proton chain. Rarer neutrinos can come from other paths, including reactions that play a smaller role in the Sun but a larger role in heavier stars. By studying these particles, researchers can test models of the solar interior with unusual directness. If the core were cooler, hotter, denser, or reacting at a different rate than expected, the neutrino signal would change. The particles do not describe every detail, but they narrow the truth. They are like faint grains of evidence carried outward from a place no light can reveal. The passage of neutrinos also changes the emotional scale of the Sun. Sunlight seems to arrive from above, but neutrinos arrive from every daytime direction through the body of Earth, and at night they still pass through the planet from the direction of the hidden Sun below the horizon. Earth is no real barrier to them. The planet is almost transparent to their passage, just as the Sun is almost transparent after they are born. This means the core is constantly sending through Earth a stream of particles from nuclear reactions at the center of the star. They do not burn, push, or noticeably alter ordinary matter. They simply pass, leaving almost nothing behind. The same core that gives daylight through slow-traveling radiation also sends a far quieter rain that hardly touches the world at all. It is another way the Sun is present, less visible than light, and more direct than light, a silent current from the ongoing fusion of hydrogen. Neutrinos are sometimes called ghost-like, and the description fits only if it remains calm. They are not supernatural. They are ordinary members of the particle world, governed by physical laws. But their behavior feels strange because matter is usually imagined as solid and resistant. A particle that can cross a star challenges that instinct. In the deep structure of nature, solidity is not absolute. Matter is mostly space at the scale where particles move, and forces decide what interacts with what. The neutrino belongs to a class of particles that rarely notices the substances that seem firm to larger bodies. Its journey from the solar core to Earth reveals that the universe is layered not only by distance and size, but by kinds of interaction. To a photon, the Sun's interior is a prison. To a neutrino, it is nearly open space. To a spacecraft, the Sun is impossible. To a particle governed by the weak force, the center is almost already exposed. This is why the deepest look inside the Sun is not made by pushing a probe inward. It is made by receiving what the core sends outward. Neutrinos do not form a picture with edges, colors, or shadows. They form a measurement, a hidden pulse of nuclear change. They show that the core is alive in the present tense, not merely inferred from ancient light. Every second, as hydrogen fuses and helium slowly accumulates, neutrinos escape as fresh evidence of the reaction. They cross the Sun before the energy of nearby photons has made even a meaningful outward step. They enter space while the light born beside them remains trapped for ages. This separation gives the Sun a double identity. Its visible surface glows with energy delayed by the interior, while its neutrino signal comes almost directly from the current center. One messenger tells of long storage, the other tells of immediate creation. The two together make the hidden star more knowable. In the quiet flood of neutrinos, the solar core is no longer only a theoretical depth. It becomes a source that can be listened to, not with ears, but with vast detectors waiting in darkness for rare sparks. From those sparks comes knowledge of the unseen engine, the rate of fusion, the presence of nuclear pathways, and the fact that the Sun continues to hold its balance at the center. The ghost particles do not illuminate the core in the visual sense. They do something subtler. They prove that deep inside the star, beyond all reachable layers, matter is changing into energy at this moment. While sunlight takes the long road, neutrinos carry the immediate news from the dark. For many years, the Sun sends out a message that seems too faint. The theory of the solar core says that fusion must produce neutrinos in known amounts, because the same proton-proton chain that powers the star also releases them as part of its first steps. If the core is working as understood, a steady flood of electron neutrinos should reach Earth in numbers estimated from the Sun's brightness and nuclear physics. The idea is simple in outline, but its test becomes one of the most delicate experiments in modern science. The particles almost never interact, so a detector must wait for rare traces inside huge volumes of material, often buried deep underground to escape the noise of other particles from space. When the first long searches begin to count solar neutrinos, the result is not empty silence. Neutrinos are found. The core is speaking, but it speaks more softly than expected. Detectors see fewer solar neutrinos than theory predicts. And the difference is large enough to become a real mystery. The missing particles form what becomes known as the solar neutrino problem, a quiet puzzle at the center of the Sun and at the edge of particle physics. At first, the deficit seems to offer several possible meanings, none of them small. Perhaps the solar model is wrong. Perhaps the core is cooler than scientists think, or fusion is proceeding differently, or the Sun's internal structure has been misunderstood. Since neutrino production is sensitive to conditions in the core, a shortage could point to a hidden flaw in the deepest picture of the star. Yet the Sun's visible behavior, its mass, its radius, its brightness, and the study of solar vibrations all support the broader model of a stable main sequence star powered by hydrogen fusion. The theory is tied to many independent measurements. If the model is deeply wrong, then more than neutrinos must be explained. The Sun continues to shine with the expected steadiness. Its internal sound waves reveal a structure close to the predicted one. Its age and luminosity fit the long story of stellar evolution. The problem, therefore, grows more intriguing. The missing neutrinos may not be missing because the Sun fails to make them. They may be missing because they change on the way. This possibility leads into the hidden identity of neutrinos themselves. In the first picture, a neutrino made in a solar reaction is an electron neutrino, one member of a family of related particles. Other kinds are known as muon neutrinos and tau neutrinos. These kinds are called flavors, not because they are substances to taste, but because particle physics needs a way to name their different forms of interaction. Early solar neutrino experiments are mainly sensitive to electron neutrinos. If a solar neutrino remains an electron neutrino from the core to Earth, then those detectors can count it in the expected way. But if the neutrino changes flavor during its flight, then a detector looking mostly for the original kind will record a shortage, even though the total number of solar neutrinos remains correct. The particle has not vanished. It has altered its form. This idea is called neutrino oscillation. It means that neutrinos can shift among their flavors as they travel. a behavior possible only if they have mass, however tiny that mass may be. The mystery of the Sun therefore becomes a discovery about the particle world. A puzzle born in the solar core points beyond the star and reveals that neutrinos are not as simple as once assumed. The solution develops slowly through better experiments, deeper detectors, and more careful separation of signals. Some detectors measure the electron neutrinos from the Sun and continue to see the shortage. Others become able to measure the total flow of solar neutrinos across flavors, or to compare different kinds of interactions. The crucial pattern emerges. The number of electron neutrinos arriving at Earth is lower than the number produced in the core, but the total number of neutrinos, including those that have changed flavor, matches the expectations of solar fusion. The Sun is not underproducing energy. Its core is not dim in the way the early counts seem to imply. Instead, the neutrinos are transforming during their journey through space and matter. The missing signal is not lost from the universe. It has moved into forms that the earliest instruments could not fully see. In this way, the solar neutrino problem becomes one of the most elegant reversals in science. An apparent failure in the understanding of the Sun becomes confirmation of the Sun and correction of particle theory. The star remains steady. The particles turn out to be stranger. This resolution strengthens trust in the deepest model of the Sun. Since neutrinos come almost directly from the core, their agreement with fusion theory is powerful. They are not delayed like photons. They do not spend ages diffusing through the radiative zone. They leave the core as fresh byproducts of nuclear reactions and arrive at Earth with only the short delay of crossing space. When their full behavior is understood, they reveal that the expected fusion rate is truly occurring. Hydrogen is becoming helium in the hidden center. The proton-proton chain is working. The energy budget of the Sun is consistent with nuclear physics. The solar core is not visible, but it is measured through its ghost particles with an intimacy no telescope can provide. The neutrino mystery therefore deepens the deepest look inside the Sun, because it shows that the core contests not only stellar theory, but the basic properties of matter. A star becomes a laboratory larger and older than any built on Earth. The solution also shows why indirect evidence must be handled with patience. The first shortage is real. The detector's not simply wrong. The theory of fusion is not simply wrong either. The interpretation is incomplete because the particles themselves have a hidden behavior. This is a gentle lesson in scientific uncertainty. When observation and theory disagree, the disagreement does not immediately declare one side false. It opens a space where assumptions can be found. In the solar neutrino problem, the assumption is that neutrinos keep the same flavor after being produced. Once that assumption changes, the pieces align. The Sun's core, the detectors on Earth, and the rules of particle physics become part of one continuous explanation. The missing neutrinos return, not as a count of the same particles in the same form, but as a fuller understanding of their journey. There is something quietly fitting about this. The particles that barely touch matter also refuse to remain simple. They pass through the Sun almost freely, pass through Earth almost freely, and even in identity they are not fixed in the old way. They are messengers, but they are changing messengers. By the time they reach a detector, they carry information about two realms at once, the conditions of the solar core that made them and the quantum rules that shape their travel. Their path from the core to Earth becomes a bridge between stellar physics and the smallest known particles. The Sun is no longer only an object to observe in the sky. It is a source of experiments crossing every second through the planet, through laboratories, through rock, water, and living matter, usually without trace. The neutrino mystery also preserves a sense of humility about the core. Even when the broad picture is confirmed, the Sun is not made simple. It remains a hidden engine whose messages arrive in altered forms. Photons lose their original identity in the maze of plasma. Neutrinos keep their direction more faithfully, but shift their flavor. Every messenger from the center carries both truth and transformation. To understand the core, science must learn how each messenger changes on the way out. Light must be interpreted through radiation transport. Neutrinos must be interpreted through oscillation. Solar vibrations must be interpreted through waves moving inside a fluid star. No single clue gives the whole picture alone. Together, they create a view of a place that cannot be seen directly. The old shortage of neutrinos could have suggested a failing sun, a core not hot enough, a star somehow less active than its light implied. Instead, it leads to a calmer and deeper result. The sun is shining as expected, and the universe is subtler than expected. The core continues its steady fusion, producing neutrinos with every successful step in the chain. Some begin as electron neutrinos and arrive as something else. A detector may catch only a rare signal, a faint trace inside darkness. But that trace belongs to a story that begins at the center of the star. The mystery does not end by making the sun less strange. It ends by widening the strangeness. The deepest look inside the sun reveals a hidden core that works, and a particle world that changes while crossing the quiet distance between star and Earth. Beyond the main path of solar fusion, there is another route hidden in the core, quieter in the sun than the proton-proton chain, but deeply important for understanding stars. It is called the carbon-nitrogen-oxygen cycle, often shortened to the CNO cycle. In the sun, this cycle contributes only a small share of the total energy, because the core is not hot enough for it to dominate. The proton-proton chain remains the main engine, turning hydrogen into helium through a sequence suited to a star of the sun's mass. Yet the CNO cycle is not an afterthought. It is a second way for nature to reach the same broad result, and its presence reveals that the solar core is not a single simple reaction, but a network of paths shaped by temperature, composition, and probability. In more massive stars, where central temperatures rise higher, the CNO cycle becomes the leading source of power. In the sun, it remains faint, almost hidden. But because it operates through different nuclei and produces its own neutrinos, it offers another window into the core's concealed chemistry. The name of the cycle gives its secret away. Carbon, nitrogen, and oxygen are involved, but they are not consumed in the final accounting in the same way hydrogen is. They act as catalysts, meaning they help reactions proceed while being restored by the end of the cycle. The central transformation is still the fusion of hydrogen into helium. 4 hydrogen nuclei are ultimately converted into one helium nucleus, and energy is released from the small difference in mass. But instead of hydrogen nuclei mostly meeting one another directly in the proton-proton chain, the CNO cycle uses heavier atomic nuclei as stepping stones. A carbon nucleus captures a proton. Through a sequence of reactions, it becomes nitrogen, then oxygen, then returns toward carbon again, while helium is produced and energy is released. The cycle is like a hidden turnstile in the plasma, allowing hydrogen to pass through a chain of heavier nuclei before emerging as the same final product of stellar fusion. This heavier route is strongly sensitive to temperature. A small rise in core temperature can increase the CNO reaction rate dramatically, much more sharply than it increases the proton-proton chain. This is why the cycle dominates in stars more massive than the Sun. Their greater gravity compresses their centers more strongly, raising central temperatures enough that the CNO pathway becomes efficient. Such stars shine more intensely and live shorter lives, because their cores burn through hydrogen at a faster pace. The Sun, by contrast, is cooler at the center than those heavier stars, and so the proton-proton chain remains better suited to its conditions. The CNO cycle still occurs, but only as a minor contribution to the sun's luminosity. Its faintness makes it easy to miss in a general picture. Yet its existence matters because it connects the sun to the wider family of stars. The same core that gently powers Earth's daylight also contains a trace of the process that rules hotter stellar hearts. The CNO cycle also depends on elements heavier than hydrogen and helium. Astronomers often call these heavier elements metals, even when they are not metals in the everyday sense. Carbon, nitrogen, and oxygen were not made in the first moments after the universe began. They were built by earlier generations of stars and spread into space by stellar winds and explosions before the sun formed. This means that the small CNO contribution inside the sun carries a memory older than the solar system. The cycle uses nuclei created by earlier cosmic history to help power a later star. In the core, carbon and nitrogen are not merely chemical labels from living worlds and atmospheres. They are nuclear participants, remnants of previous stars serving as catalysts in the present sun. The deepest look inside the sun therefore reaches backward into the ancestry of matter. The solar core is not made only from the simple hydrogen born near the beginning of the universe. It also contains traces of heavier elements forged in vanished stars, and those traces leave faint signatures in the way the sun shines. For a long time, the CNO cycle in the sun is expected from theory, but difficult to confirm directly. Its energy contribution is small, and the photons produced by fusion cannot preserve a clear label showing which reaction made them. By the time energy escapes as sunlight, it has been scattered, absorbed, and remade too many times for such a distinction. Neutrinos again become the key. Just as the proton-proton chain produces neutrinos, the CNO cycle also produces neutrinos with characteristic energies. Because neutrinos escape the core almost directly, they can carry evidence of the reactions that created them. Detecting CNO neutrinos is extremely difficult, because the signal is faint and must be separated from other solar neutrinos and background events inside the detector. Yet this faintness is precisely what makes the detection so meaningful. It is not merely another count of particles. It is a way of hearing a smaller nuclear voice beneath the dominant song of the proton-proton chain. Experiments designed to catch solar neutrinos must work in darkness, shielded from much of the noise that rains down from space. They wait for rare interactions inside carefully purified materials, where even a trace of natural radioactivity can confuse the signal. To identify CNO neutrinos, the detector must distinguish an uncommon pattern from other particles produced by the sun and by the Earth itself. When direct evidence of CNO neutrinos is found, it gives science a new confirmation that the secondary fusion path is truly operating in the solar core. The detection does not overturn the picture of the sun, it refines it. The sun remains a proton-proton star, but now its quieter pathway is measured more directly. The core becomes more detailed, less like a single hidden flame, and more like a layered nuclear environment where several processes occur at once, each with its own weight in the total energy budget. This matters beyond the sun because the CNO cycle is central to stellar evolution across the galaxy. Massive stars depend on it, and massive stars are the factories that shape much of cosmic chemical history. They live fast, shine brilliantly, and end in ways that return heavy elements to space. Understanding the CNO cycle in the sun, even as a minor process, helps test the same physics that explains those hotter stars. The sun provides the nearest and most stable laboratory for a reaction network that becomes dominant elsewhere. Its core is easier to study than the core of distant massive stars, not because it is easy, but because it is close enough for neutrinos, vibrations, light, and gravity to be measured with great care. A faint process in the sun can therefore illuminate a powerful process in other stars. The cycle also offers clues about the Sun's composition, especially the amount of carbon, nitrogen, and oxygen in its interior. This question connects to a deeper challenge known as the solar abundance problem. Measurements of the Sun's surface composition and models of its interior have not always fit together perfectly when compared with helioseismology, the study of waves inside the Sun. CNO neutrinos can help because their production depends on the abundance of the elements that drive the cycle. A better measurement of these neutrinos may sharpen the picture of what the core contains. In this way, the faint particles are not only evidence of a reaction, they are clues to the ingredients of the hidden center. They may help reveal whether the surface tells the full story of the Sun's deep composition, or whether the interior keeps subtler differences that still need to be understood. The CNO cycle therefore adds a different kind of intrigue to the deepest look inside the Sun. It is not the main source of sunlight, so it does not carry the grand simplicity of the proton-proton chain. It is smaller, quieter, more dependent on rare elements and sensitive measurements. Yet its quietness makes it valuable. It shows that even in a star often described as ordinary, the core contains layers of hidden structure. The Sun is simple enough to shine steadily for billions of years, but not so simple that one reaction tells the whole story. Beneath the brightness, there are dominant paths and minor paths, common neutrinos and rare neutrinos, hydrogen from the early universe and heavier nuclei from earlier stars. The core is not only transforming matter into energy, it is preserving a record of how stars make and reuse the elements. In the faint signature of the CNO cycle, the Sun reveals itself as part of a much larger stellar story, where every quiet reaction belongs to the chemistry of the cosmos. The Sun appears steady because human lives are brief, but the core is not fixed. It is changing in the only way a star like the Sun can change during its long main sequence life, quietly, deeply, and almost beyond notice. At the center, hydrogen is being turned into helium, one chain of reactions after another, and every successful fusion event slightly alters the composition of the region that makes the Sun shine. The change is not dramatic from one day to the next, or from one century to the next. The visible disk remains familiar, the seasons continue, and Earth receives a flow of sunlight stable enough for oceans, air, and life to keep their rhythms. Yet under that apparent constancy, the core is slowly rewriting itself. It begins its life richer in hydrogen. It continues by spending that hydrogen. It becomes, over immense time, a center with more helium, different density, and a gradually shifting balance between gravity and pressure. The Sun is stable. But its stability is not stillness. It is a long transformation moving so slowly that it resembles permanence only from a nearby planet. This is one of the quietest facts about the solar core. Fusion does not simply produce light, it changes the star that produces it. Hydrogen is the fuel of the main sequence, but fuel is not spread equally through the Sun in its usefulness. The core is the region where temperature and pressure are high enough for fusion to occur at a meaningful rate. Hydrogen outside that central region may be abundant, but much of it is not hot or compressed enough to join the same nuclear process. The Sun, therefore, does not consume all of its hydrogen at once. It draws its long brightness from the central supply, where protons can pass through the narrow gates of the proton-proton chain. As helium accumulates there, the core's mixture changes. Helium nuclei are heavier than hydrogen nuclei, and they do not support the same number of freely moving particles for the same amount of mass. This matters because pressure in the core depends strongly on the motion and number of particles. As the mixture becomes richer in helium, the old balance must adjust. Gravity does not stop pressing inwards simply because the star has been shining for billions of years. It continues to demand support, and the core continues to answer. but the answer slowly changes. The growing helium concentration makes the central region contract slightly over time. This contraction is not a collapse in the sudden sense. It is a gradual tightening, a slow inward adjustment that raises the core's temperature and density. Higher temperature and density allow the remaining hydrogen to fuse somewhat more readily. As a result, the Sun's energy output slowly increases during its main sequence life. The change is small across human history, but large across geological time. A planet orbiting the Sun experiences not a perfectly constant star, but a star that has been brightening with age. Early in Earth's history, the Sun is believed to have been dimmer than it is now, yet Earth still develops oceans and eventually life. The core's evolution is therefore not isolated from planetary history. A slow change in the hidden center becomes a changing condition for every world in sunlight. Helium itself waits in the core like an ash that is not ash in the ordinary sense. It is not waste from combustion, because the Sun is not burning chemically. It is the product of nuclear fusion. The more tightly bound nucleus left behind after hydrogen has released part of its mass as energy. Under the present conditions in the Sun's center, helium does not yet fuse in a sustained way. It requires still higher temperatures to begin its own major reactions, so it gathers. The core becomes more helium-rich while hydrogen fusion continues around and within the changing central mixture. This build-up is the hidden clock of the Sun. No clock face turns, no surface line marks the loss, and no observer sees the central composition directly. Yet the helium abundance records the passage of stellar time. Every second of sunlight leaves a trace in the core's chemistry. The balance of hydrostatic equilibrium continues, but the terms of the balance slowly evolve. The pressure required to support the star is set by gravity and mass, while the pressure available depends on temperature, density, radiation, and particles. As the core composition shifts, the Sun compensates through structure. It becomes a little brighter, its outer layers respond, and its future path is set by the gradual exhaustion of central hydrogen. This is why the Sun's calm is not eternal. Main sequence stars are steady because they fuse hydrogen in their cores, but that stage lasts only as long as the core can maintain the right fuel supply and pressure support. For the Sun, this stage spans roughly 10 billion years in total, and it is now around the middle of that life. The Sun has already changed, and it has much more change ahead. Its present form is a long chapter, not the whole book. The future begins quietly inside the same core that now makes daylight. As hydrogen becomes depleted in the very center, fusion there eventually weakens. Gravity then gains a stronger role, compressing the helium-rich core. Around that core, hydrogen can continue to fuse in a shell, releasing energy outside the exhausted center. This shell burning changes the structure of the star. The outer layers respond by expanding and cooling at the surface, and the Sun begins the path toward becoming a red giant. That stage still lies billions of years in the future, but its cause is already being prepared in the present. The future red giant is not a separate destiny imposed from outside. It grows from the slow accumulation of helium now taking place in the core. The same process that gives the Sun its steady light also ensures that the steady phase cannot last forever. Stability becomes the pathway to transformation. For Earth, this long evolution carries profound consequences. The Sun's gradual brightening affects the energy received by the planet over deep time. Life and climate respond within a narrow range of conditions, and the long-term future of Earth is shaped by the increasing luminosity of the star. Long before the Sun becomes a red giant, changes in solar brightness may place heavy stress on oceans, atmosphere, and surface habitability. These events are distant on human timescales, but they follow from ordinary stellar evolution rather than sudden cosmic disaster. The core is gentle in the present, but its slow chemistry has planetary meaning. It sets a background trend against which atmospheres must adapt or fail, yet the core does not hurry. It proceeds according to nuclear rates, gravity, and the supply of hydrogen left in the centre. The idea of a changing core also gives a deeper meaning to solar age. The Sun is not old simply because time has passed around it. It is old because its interior composition has been altered by its own light. A young Sun and the present Sun are not identical engines. The young core holds more hydrogen and less helium. The present core is hotter and denser than it once was. The future core will become still more helium-rich until hydrogen fusion in the centre can no longer carry the same burden. A star ages from within. Its surface may show activity, spots, flares, and cycles, but its deepest aging is hidden in the nuclear ledger of the core. This ledger is written in helium, temperature, density, and pressure, not in visible wrinkles or sudden scars. The slow change also reveals why the Sun can feel both reliable and temporary. It is reliable because its self-regulating balance smooths short-term disturbances. It is temporary because the balance depends on fuel that is being transformed. There is no contradiction between these truths. A candle is temporary because it burns quickly, but the Sun is temporary because it shines slowly. Its lifetime is vast, yet not infinite. The same fusion that holds gravity back gradually removes the hydrogen needed to keep doing so in the same way. The core is therefore a place where endurance creates its own ending. Every moment of stability is also a moment of consumption. Every release of light is also a small step toward a different star. For now, the hidden center remains in its long middle phase. Hydrogen still fuses, helium slowly gathers, pressure still answers gravity, and the Sun continues to warm the worlds around it. The deepest look inside the Sun does not reveal an object frozen in perfect balance. It reveals a living stellar process, calm only because its changes are spread across ages. The core is not merely the birthplace of daylight. It is the place where the Sun's future is being prepared, one quiet nuclear reaction at a time. The visible Sun seems to begin at its bright surface, where light finally escapes into space, but the true beginning lies far below that glare, in the hidden core where no direct sight can enter. The photosphere gives the Sun its face, the corona gives it a faint outer crown. Flares and prominences reveal its restless magnetic life. Yet all of these depend on a deeper source, a central engine buried under layers of plasma and time. The core has no colour in the ordinary sense, because no eye could survive there, and no clean image can leave it. It has no quiet emptiness, because particles crowd every small volume under pressure beyond common thought. It has no solid ground, because atoms themselves have been stripped apart. Still, from that unseeable place comes the steady energy that makes the solar system bright. The core is the birthplace of daylight, not as a poetic idea, but as a physical truth. Every dawn, every warm stone, every glimmer on water, and every green leaf in sunlight begins with nuclear change in the centre of a star. This hidden origin gives the Sun a double nature. To the planets, it is a visible presence, a disk of light moving through skies as worlds turn and orbit. To physics, it is a self-gravitating sphere of plasma, balance between inward pull and outward pressure. The familiar Sun is therefore only the surface expression of an interior fact. Gravity presses the star inward. Fusion in the core releases energy. That energy helps sustain pressure, and pressure resists collapse. For billions of years, this balance has endured. It is not perfect stillness, and it is not eternal. It is a long-working equilibrium, stable enough to support life across deep time, yet slowly changing as hydrogen becomes helium. The daylight that feels simple is tied to this hidden negotiation. It is gravity, quantum physics, plasma, and time arriving softly at the surface of Earth. The path from core to daylight is also a path of transformation. Hydrogen nuclei begin as protons moving through an extreme plasma. Most encounters do not lead to fusion, because electrical repulsion keeps like charges apart. Only a rare few pass through the narrow possibility opened by quantum tunneling and the weak nuclear force. Those rare successes begin the proton-proton chain, and step by step helium forms. A small amount of mass becomes energy. Some of that energy joins the thermal life of the plasma. Some leaves as neutrinos, escaping almost directly, carrying immediate evidence from the center. Much of it begins a long confinement as radiation, scattered again and again until its first identity is lost inside the star. The sunlight that later reaches space is not a simple beam shot from the core. It is the remade descendant of energy born there, softened by the radiative zone, carried by outer motion, and released from the photosphere into darkness. This long delay changes the meaning of brightness. Light seems quick because it crosses the distance from the sun to Earth in minutes. But inside the sun, energy may wait through ages. It wanders through dense plasma where every direct path is broken. It passes through a maze without walls, guided only by the statistical flow from hotter depths toward cooler outer layers. At the surface, the same energy finally enters open space and becomes part of the expanding radiation field of the star. Most of it travels outward forever, missing every planet. A tiny part meets Earth, where air scatters it into blue sky. Clouds reflect it. Oceans absorb it. Ice sends some of it back to space, and living cells capture a portion in the chemistry of photosynthesis. The core does not know these outcomes, yet they follow from its work. A nuclear reaction in darkness becomes climate, weather, food, color, and the rhythms of life. Earth is not warmed by the core directly. It is warmed by the moderated result of the entire sun. This matters because the raw conditions of the core are hostile beyond imagination, while the energy reaching Earth is gentle enough, at the right distance, to support complexity. The sun transforms its own violence of scale into steadiness. The dense interior delays the energy. The outer layers reshape it. Space spreads it. Earth receives it selectively, absorbing some and reflecting some, building a planetary energy balance. Life exists within that balance, not because the sun is mild at its center, but because the path from center to surface and from surface to planet filters the core's power. The birthplace of daylight is therefore not a lamp. It is a chain of moderation. It begins in nuclear fusion and arrives as warmth on a world protected by atmosphere, distance, and the star's layered structure. The core also links the present Earth to the deep history of the solar system for billions of years. It has provided the energy around which planetary environments evolve. Early Earth receives light from a younger sun that is dimmer than the present sun. Oceans, rocks, air, and life respond to changing conditions while the core slowly grows hotter and more helium-rich. Across ages, the sun brightens, not suddenly, but as a consequence of its own interior evolution. The same hidden center that makes life possible also shapes the long boundaries of habitability. In the far future, the core's changing composition will end the sun's present stability. Central hydrogen will become depleted, the balance will shift, and the star will move toward a red giant phase. The inner solar system will be transformed. Yet that distant future is prepared by the same quiet process that now lights every morning. The core's gift and the core's ending are inseparable. Every second of sunlight spends a little of the sun's central hydrogen and adds a little more helium to the star's inner record. Still, The Sun's present age is one of endurance. It is not near the end of its main sequence life on human terms. It continues its slow work with a steadiness that makes the days feel ordinary. This ordinariness is itself remarkable. A star is not required by nature to be gentle, long-lived, and well-placed for a planet like Earth. Many stars are smaller and dimmer. Many are larger, brighter, and shorter-lived. Some live in crowded systems. Some flare strongly. Some change too quickly for long-surface stability nearby. The Sun is not unique in the universe, but it is the local star whose balance becomes the background of earthly existence. Its core sets the tempo. Because fusion proceeds slowly, the solar system receives an extended era of light. Because the Sun is massive enough to shine strongly, but not so massive that it burns quickly, a planet has time for oceans, chemistry, evolution, and memory. The deepest look inside the Sun therefore becomes a way of seeing Earth differently. The blue atmosphere, the moving sea, the growth of forests, and the warmth held in soil are not separate from stellar physics. They are the outer consequences of hydrogen fusion under pressure. The softness of a sunlit landscape is connected to particles in a plasma too extreme for matter to remain atomic. The calm light on a sleeping world begins in a place where pressure and heat erase every familiar form. This connection does not make the world less gentle. It makes gentleness more astonishing. Nature carries energy from an almost unreachable center and spreads it until it can become the quiet background of life. Even the hiddenness of the core adds to its meaning. The most important engine in the solar system is not the most visible part of it. The surface shines, but the surface is a release point. The core creates. It cannot be photographed directly, yet it announces itself through sunlight, neutrinos, solar vibrations, and the long survival of the star. Its existence is inferred with confidence because many different clues agree. The Sun's structure, its energy output, its particle messengers, and its slow evolution all point inward to the same central truth. Deep inside the Sun, hydrogen is becoming helium, mass is becoming energy, gravity is being answered by pressure, the planets are being warmed by a balance they never see. The solar core remains both known and unreachable. It is measured, modelled, and listened to through ghost particles. But it is never opened like a chamber. It stays buried beneath the star's own brightness, turning matter into the energy that crosses space. Every beam of sunlight carries that hidden origin without revealing it directly. It arrives silently, after ages of delay and minutes of flight, and touches the solar system with the outward result of a deep central transformation. The birthplace of daylight is dark to direct sight, but bright in every consequence. It is the reason the sun shines, the reason Earth is warm, and the reason the morning sky is connected to the deepest heart of a star.